so you have a real non-negative spectrum. You had a question?
Yeah, my question is about the mean subtraction. If you have a stationary flow, of course, but if your flow is not stationary and so your mean is not converged, what is your point of view about that?
Good point. The question, there's another reason why you should remove it. And the assumption which I make was that we have stationary boundary conditions. For instance, you have a cylinder wake, you have the no-slip condition on the cylinder, and you have uniform flow at infinity or far away. So the mean flow now takes away the uniform flow condition. And the remainder, U prime, satisfies the homogeneous Dirichlet condition. And if U prime satisfies the homogeneous Dirichlet condition, that means all the fluctuation must fulfill it. That means the POD mode must fulfill it. And now you can, in the expansion, you can choose the POD mode amplitudes arbitrary. And that's what you want. You want a Galerkin system without constraints. So this is what you have to do to arrive at this point. Good. So now you have the eigenmodes, and essentially what the POD mode is, the POD mode is nothing but a linear combination of your snapshots done in a smart way. And of course, the more snapshots you have to rescale it somehow, and you remove some of the fluctuation intensity in the direction. So at the end, you have also normal modes. And you can check this also by looking at the trace. So that the sum of the trace of the correlation matrix should be the sum of the eigenvalues, should be the average fluctuation energy in the flow. So these are the POD modes. And now you have the AIs. And these are the amplitudes, again, are somewhat proportional to the modes. So if we have again a couple of properties, so the POD modes can be obtained by projecting the fluctuation on UI. The average should be 0, and the second moment should be centered. So you have not only also normality in space, you have also orthogonality in the frequency. In the POD mode domain. Good. Now we go one step further. So what can we do having this fluctuation? We can get a lot of inspiration when we look at Munin-Yaglom. And so all the equations which you see there, where you have the flow decomposed in a mean flow and a fluctuation, can be written much more accurately in terms of a POD mode basis. So we start now with the Reynolds decomposition. I will remind you of an equation which you should know from the from fluid mechanics. The Navier-Stokes equation is written like this. The Reynolds equation is essentially the residual with the Reynolds decomposition equals to 0. A weak formulation means you take the residual and you can multiply it with any test function, and you should get 0. Why is this effort? Well, you can include, for instance, now shocks in your solutions. And if you multiply the residual with U prime, then you get an interesting equation. You get the equation of fluctuation energy. And here you see the Navier-Stokes equation. It can be expanded with a Reynolds decomposition. Now it looks something like that. So it always has some constant and linear quadratic terms here, a constant and linear terms here. If you average them, these are the survivors here. So this is a Reynolds equation. If you now subtract the Reynolds equation from the Navier-Stokes equation, you get an equation for the fluctuation energy. If you multiply this now with U prime, you get these volume integrals. So this essentially is your production term. So this leads to the production term. This leads to the convection term. This leads to the transfer term. This leads to the dissipation. And this leads to the pressure power. So just a reminder of your Navier-Stokes of fluid mechanics lecture. Now we can do the same thing with the modes. Here's a picture, the fluctuation. There's one term called production, so this essentially determines how much energy the fluctuation gets from the mean flow. There's one term called dissipation. This is how much energy the heat reservoir or the molecular structures get from the coherent structure. And there are two terms which are determined by the boundary. One is the pressure power and one is the convection. So in an infinite domain, a periodic pipe and so on, these terms would vanish. And now you can do the same thing also with, you can do the same thing mode-wise, but what you have to do now, you have to expand U prime in terms of the Galerkin expansion. Instead of projecting this residual on U prime for the global energy balance, you project it on AIUI. And what you see immediately from the structure, if I'm adding up all these contributions here, then this becomes U prime. And essentially this gives a basis why we interpret this as a modal energy flow balance. There's another equation which is vital. If you project it on UI, we again get the Galerkin system. And as seen in my last lecture, the Galerkin system has some linear term, it has some quadratic term, and it also has some pressure related term. Just, you can make many more variations with this. For instance, you can, in principle, project the residual on EX, the unit vector in X direction, and this gives you the equation for the drag. So now you are capable of explaining the drag in terms of your Galerkin expansion, or you can multiply it with EY, then you can interpret the lift, you can look at the Reynolds stress term and so on. So there's a lot of equations which you can derive just with this simple ansatz. Here I want to focus just on the modal energy analysis. We do again the analysis here and here. The Galerkin system looks like that. And if we multiply with AIUI, we get these terms using all the POD properties. So there's one term left over, this one here, which leads to the production. There's another term from the Galerkin system times the energy leading to the convection term. There's a irreducible term, essentially this is the essence of turbulence, which leads to the transfer term, and dissipative term, and some other terms. You see that the modal production, convection, and dissipation scale are proportional to the fluctuation energy in each of the modes, and the Galerkin system essentially determines something like the gain, and these nonlinear terms are the one which are the troublemaker. The picture which now emerges is the following. So you have the different modes here. There are some terms, essentially they get some energy from the mean flow, lose it to the dissipation, they lose it at the boundary. The most important thing is the transfer term. If you remove the transfer term, the nonlinearity, maybe the first mode will explode. The modes will either explode or they will decay. You have no sociology. So you need the nonlinearity in order to have this sociology. And here this is just the remainder that the averaged global energy flows are the sum of the modal flows, and they all should add up to zero. And so this is the recipe now. So you have something like M snapshots. You have to write routines essentially for these three things, for an inner product, for a trilinear form from the convective term, a bilinear form which comes from the dissipative term, and maybe you want to consider the pressure power as well, then you need the surface integral. Compute the mean flow, compute the correlation matrix, determine the spectral analysis, compute the POD modes, compute the Fourier coefficients. You see these operations are very simple, and if I show you my Fortran code, it's only something like 3 pages long. So as an augmentation, you can look at the dynamics. So this is your dynamical system after the Galerkin projection. You can perform a modal analysis for each of the modes, and the modal analysis will tell you, for instance, what is anything is missing in your in your approach. For instance, you can see from Fi if you should include the pressure term. You can see from the difference to 0 if you should add some stabilizing terms and so on. Any questions so far? Oh. you have to choose. So again, hands up. I will try to start from here.
Questions?
No. Good. So I've shown you now a procedure which I think most of you can program easily yourself, say on one weekend. Does it typically work or not? Well, there are a couple of things which you should keep in mind. There are some things which make your which you may have to add to stabilize your Galerkin system. The first thing is maybe you are missing some modes in the POD which are stabilizing. So in my first lecture, I've shown the shift mode. If you don't add the shift mode to the POD Galerkin model, it will be inherently fragile and potentially inrobust. So the shift mode is one possibility. Essentially, this is a difference from the steady solution to the mean flow. Now, there's another aspect which Steve has mentioned. You can derive from the Navier-Stokes equation, from most boundary condition, that the quadratic term should be energy conserving. And that said, it's energy conserving if the contribution at every instant to the whole fluctuation energy is 0. And you can show that this coincides with another condition. So you can decompose the Qijk, so the 3 tensor, in one quantity, which is the average, and another quantity, which is the remainder. So you need to remove this part because you will always have some numerical error to be Navier-Stokes consistent. This is the remaining part, and this often stabilizes an otherwise unstable Galerkin system. Because the further you go with your mode number, the smaller structures you have, the larger the numerical error, and at some point you will inevitably get noise.
I have a question concerning the shift mode. In case you have a transient problem, for example,
okay,
is it to be meant in terms of simply low frequency, or is it to be meant in terms of ensemble averaging? And if it is in the first case, how do you choose how low is low frequency?
Good question. Now, we've written one paper where we showed 4 different definitions of the shift mode. And for instance, you can say it's the difference between the steady solution and the mean flow. Nice. You can say the shift mode is the one which you derive from the Reynolds equation. So essentially, you look at the linearized Reynolds equation and look at the fluctuation. So in which direction would you go based on the Reynolds stress? This would be another way. Another possibility is you take away the fluctuation and you look what remains. So now your shift mode is the first POD mode of the low frequency remainder. You can also take the one frequency average. So it's left to your engineering ingenuity. And there are many possible choices, but most of them lead to Rome. And even the first model, the model of Nadine Aubry, has included something like the shift mode. So essentially, she has always recomputed the mean flow, the base flow, as a function of the fluctuation which she has resolved. So she had the cubic terms explicitly in her approach. Good. Now there's something which may be a little less known. You can look at your Galerkin system, and without any integration, you can say you have a necessary and sufficient condition if all your solutions are globally bounded. Of course, we agree, this is desirable, right? You don't want to go to infinity, because the further you go away from the origin, the less physical your model will become. So there is a condition for boundedness, which has been derived by Michael Schlegel. And I can tell you the essence of the coherence. It's really analytically very beautiful. So a sufficient condition is the following. If you find one point in the state space where the linearized Navier-Stokes equation, the linearized Galerkin system is stable, then it guarantees boundedness. So there's a very easy way to test the sufficient path, and the necessary path is difficult to prove, so I could not have done it. Another point, we can also play with a nonlinear model eddy viscosity, which I will introduce later, and under some conditions it also guarantees boundedness. And if you want to know any more tricks, there's an expert in the front row. There are many more tricks which could be useful. And now we go to get our hands a bit dirty with a small tutorial, xROM. So at some point it was called xAMC, but it has been completely rewritten. So you go the standard path of the Galerkin system. You include some additional calibration, which includes something like a modal eddy viscosity, and it scales with the fluctuation. It has to scale with the fluctuation energy. There are strong arguments for that. So this system has many features for large volume data processing and flows, most common in grids, parallelizable, and so on. So if you want to have more than, say, 100 2D snapshots, but have a high volume, this may be a path you may want to go. And of course, there's a documentation around it. And now I want to show it to you. So now I can't show it to you anymore. No, I'm kidding. so here's the package. You have to unzip it. You find the link on the chapter. So you see something has been unloaded. There's something which is a package. I'm a bit excited. So I've tried it something like 10 times, and I was successful in half of the times. So now the program has become an executable, and now I let it run, and probably now it needs something like 2 minutes. So Daniel has written such a good wrapper around it that I get scared of my former code. So here, essentially, you have to click what you want. So this is here. Now you have computed the POD. Cool, isn't it? We can go a bit further. And so here you find a configuration file. So now I say I get ambitious. I say, okay, we have the Galerkin expansion. I also want to get the dynamical system. And to save a bit time, I also include where is it? Why can't I go lower? Oh, here it is. Good. So my kids don't allow me to use the computer anymore, so I'm a bit struggling. so one of Steve Brunton's postdocs asked me, Jibai, with which software do you solve your scientific problems? And I explained to her, email. There's an upgrade to this. So there was a Nobel Prize winner who was cloning one of the sheeps, and he was asked how he does his work, and he says he does cloning by phoning. So the next level is you use your cell phone. Of course, you need a good database, an address database over there. The same data which almost everybody is approximately using. Good question. It's a cylinder wake data for one period. So now we need to wait a bit, maybe 1 more minute, and then I can show you what we have computed.
To summarize a bit what the code is doing, so you're computing the POD modes from a set of snapshots of a...
Yes. I just have the snapshot,
okay.
nothing pre-computed.
Then you create the dynamical system.
Then you compute the POD, and after the POD you compute the dynamical system, then you integrate the dynamical system, and then you also use calibration for the eddy viscosities.
So you produce more snapshots using the projected dynamical system, or
not more? Well, you'd use the same snapshot. I will explain the modal eddy viscosities in a second. Good. So what do you want to see? This is input data. This is not interesting. Let's look. Output data, run 1. So we managed to do it in one attempt. That's good. We have the Galerkin expansion. POD mode amplitudes. So what you see here, essentially you see the mode amplitudes. So this answers your question regarding the input. And there should be, oh, asked me to do something. Good. So now we also have the POD mode spectrum. So you see the energy, first mode, second mode, and so on. So it rapidly decays. Very simple flow. You can go to the dynamical system, and let's look what we have. So what we essentially have here, we have dynamicals. Initially is a Galerkin system, and then what the dynamical system gives us. 1, 2, 3. So you see that there's some small deviation with the higher order modes, but it's reasonably well. So this went much better than I expected. Do you have any questions? Okay, you can try it yourself. So it's a really fast code. You can use multiple meshes. And so if you have heavy volume of data, it could be interesting in the add-ons like clustering, xROM, and so on. Good. Yes?
I'm not really sure if I understood correctly, but just tell me if I'm right. What you're basically doing is start from a database, you build your POD modes,
yes.
And then you, instead of finding the evolution of the coefficients versus time projecting on the pod modes, you integrate over the pod modes and you compare with the actual solution.
First principle, you ask the Navier-Stokes equation for the dynamical system. Yes.
Okay.
Yes. So this is not data-driven approach. This is
exactly.
This is Navier-Stokes-driven approach.
Okay, very good. Thank you.
Good. So essentially, this does what I've been teaching. So I will skip these POD slides. So now we will see some examples, and we are all a fan of the cylinder wake. It's so easy. I've explained these modes already in my first talks, and we've seen them many more times. So essentially, the first pair, first harmonics, second harmonics, third harmonics, fourth harmonics, with rapidly decreasing energy. The Galerkin model works very much like sham for one operating condition. And we can learn a bit about it. If we purify our Galerkin system, and we take away non-linear terms which have a small value, then we get something like a coupled dynamical system, which looks something like that. So first harmonics, second harmonics, and so on. We also have a quadratic term, which is shown here. And now, if without a linearity, this one would explode, so the growth rate is positive, and this one would decay. So you need a social welfare system. And this is communicated by our transfer term. If you multiply this with A1 and average, you get the fluctuation energy here and the modal transfer term here. So you get these equations. You see, in order to keep these modes alive, the transfer must have the opposite sign. And the sum of the transfer term is 0. So you get as much energy out as you invest in it. So you have harmonically related oscillators with this growth rate sequence, and the quadratic coupling is energy preserving. Again, energy preservation of the quadratic term. This is another picture how to show it. Here you see the fluctuation energy again as a logarithm. First pair, second pair, third and fourth pair. These are the corresponding frequencies. These are the growth rates of each of the oscillators. So what the linear interactions, so production and dissipations do, they feed the first one and they dissipate the other modes, but the social welfare system essentially takes care that they all stay alive. And there's one aspect which is very troubling. So this sigma is something like 0.007. So we have seen already identified growth rates which are of the order of 0.1. So we are missing more than 1 order of magnitude in the growth rate. And this shows how fragile these Galerkin models are if they do not have additional stabilizers. Next thing, here we see the modal energy. First mode, second mode, this is the production. So they take energy out of the mean flow. The other modes are negligible. The dissipation also happens in the mean flow, but also in the other mode, convective term. So a lot of energy leaves the domain. And the transfer term essentially takes energy from the rich and feeds it to the poor. And there's some residual term of the pressure. And there's another way how to plot it. You can now take the production and divide it by the energy. You get something like the energy efficiency. So if you give a mode a certain amount of energy, how much energy does it extract from the mean flow and how much does it loses? So the energy efficiency here are plotted here, all get energy. The first from von Karman vortex shedding, these here from the shear layer structures. But now you see something interesting. The dissipative, the higher order modes are very good in dissipating their money, while the transfer term essentially gives them essentially the money. The convection term has little effect, and the pressure also has little effect. Essentially, here we see the Kolmogorov cascade already in a periodic flow. Now we look at another flow. Shear layer ratio, velocity ratio 3:1. Essentially what Steve has shown in this morning, but a much smaller domain. These are the streamlines of the fluctuation. You do a POD, first mode, second mode, first harmonics, second harmonics. This should not surprise us anymore. When we do the energy, when we do the Galerkin system and ignore the pressure term, essentially we get this limit cycle here for the DNS, and this is the limit cycle for the pressure term. So we are far off, and when we add the pressure term, we are again on the limit cycle. So here we need to include the pressure term. So just some warning for the practitioners. Now you can ask, why is the pressure term so important? Well, you look at the total balance. You have a production and convection. This is something like what remains now is something like 80%. And so 10% are dissipated and 10% are lost by the pressure term. So the pressure term is as dissipative as viscosity, and this is a laminar flow. And this is why we would not sacrifice the dissipation term, and hence we shouldn't also not omit the pressure term. This is a energy flow diagram, mode number 1 and 2, now combined to 3. So they get all the energy from the production. Then they lose around 10% by dissipation, 10% by pressure work, 80% by the convection and transfer. This mode is only kept alive by the energy from the first pair, and most of this gets convected and only part of that gets dissipated. So these diagrams can be rather revealing in terms of the energy flow. Now, not all the flows which we have can be fully resolved. If you have any turbulent flow, you will be lucky if you can resolve something like 50% of the fluctuation energy. So maybe you can only resolve 30% of the fluctuation energy. So you have your Galerkin expansion, and there's a residual, and you know the residual is significant, but you would like to account for it anyhow. How can you possibly do it? Well, there's a solution to that, the busyness approximation. So essentially, you use that the stochastic fluctuations take energy out of the resolved modes. How can you describe it? Well, you can describe it with an additional eddy viscosity here in the linear term. So the picture which is emerging is the following. We have some modes living from the mean flow. They don't dissipate anymore. They lose everything to the transfer term. You have some dissipative modes which you don't want to resolve, and this dissipation is modeled by this eddy viscosity here. So using a modal instead of a global eddy viscosity has been suggested by Dietmar Rempfer. You look skeptical? No. Okay, good. So here we have a large eddy simulation, flow left to right. Here we see the V component. Of course, some Kelvin-Helmholtz structures. We see a bit of vortex pairing, large eddy simulation ratio against 1 to 3. So this was a particular LES where the Reynolds number is effectively infinite. And you see some irregularities. POD mode amplitudes. The first two modes essentially describe the Kelvin-Helmholtz structures. The next two modes describe the vortex pairing. Here you see this structure becomes this structure, becomes this structure, becomes this. So you can imagine if you are moving around, you are describing a vortex pairing. And these are the POD mode energies are plotted here. And of course, you can plot more and more. At some point, you get a continuous spectrum. So again, what has been outlined earlier. So what we are doing now, we do the energy flow analysis. And now we try to keep track how much energy, excess energy, do we have in each of the modes, or not excess energy. And we compensate this by having an eddy viscosity, which takes into account that the modal energy balance should be 0. So this is a simple trick. So essentially we derive our modal eddy viscosity from our original data, and then we get already pretty good agreement between, for instance, the first POD mode amplitude in the LES and the first POD mode amplitude in the Galerkin system. And I could show much more, but this shall suffice shall suffice. So my focus on this talk is automated methods, which typically work. There's another example of, I would call it a deep mean field modeling of the fluidic pinball, which Nang Deng has derived. Now we see one reduced order model which encaptures 3 different steady states, 3 different periodic solutions, all the transitions between them. And you see this is a type of models you can not automate for a certain period of time, and you can ask none and go to his a poster. Just a small disclaimer, there are some things when the model become really beautiful, there is always some thought process behind it. Now we go to another way of presenting our data, locally linear embedding. I've briefly reported it in my first lecture. So it's a way of mapping all the high dimensional data to a low dimensional manifold and the way back. I've shown these results already in my first lecture. So steady solution, limit cycle, and here you see the transients are going outwards. And you can go backwards from these feature vectors to the original flow, and you have something like a 1% of representation error maximum. Now, if you do this locally linear embedding, you assume already you have your flow structures, and you did CFD. Now I will present you an example where we derive something similar for experimental conditions. And in experimental conditions, we have some data. Typically, the flow structures are not time resolved. There are some ensemble, but we may have some sensor signals like the lift being time resolved. And now we have to find something like a feature. So we have to lift this sensor signal so that there are no false neighbors. So if you look at neighboring states, they evolve according to the same dynamics. So if you have, for instance, a cosine t is indicative of an oscillatory dynamics. Now you look at the time delay, you have cosine t and sine t, and suddenly you can plot things in a two-dimensional state space diagram, and you can build a dynamical system. And the dynamical system is shown here. So you build your dynamical system with your sensor signal, but you use essentially the PRV data first to get a mapping from your feature vector to the flow. So this is our feature-based manifold. And then you do the reduced order model, which have been beautifully introduced this morning. In principle, you can also get POD mode amplitudes. Here we see again the lift coefficient and our phase portrait. So essentially the derivative is our way of lifting it. You see the trajectory has no crossing points, so we can fit a dynamical system here. At this point, we see in the vorticity fluctuation feed this structure. And then at this point, this structure here. So you see the structures change. This should not surprise us from my first lecture. And with Steve's Cindy, we arrive at a very simple dynamical system, which Steve has already presented. So essentially, it's something like a van der Pol oscillator, which describes our dynamics here in this plane. So now we have a system, dynamical system, for our feature vector, and we can do the mapping from the features to the velocity field. And the mapping we simply do k nearest neighbors, and this is as accurate as you can possibly imagine. And in addition, you can derive some modes, which are as good as the POD modes. So here again, structures for different times in the numerical simulation, locally linear embedding. It's perfect, so our estimator is wonderful. If you do a Galerkin expansion, you lose a lot. So essentially, this looks much more than the high amplitude states. So this is clearly wrong, and this becomes right. If you look at the residual, now we look at the residual and normalize it with the fluctuation energy over one period. So at the end, our local linear embedding gets things wonderfully right. Even with 25 POD modes, so the red curve here, we are far worse. We are more than 3 orders of magnitude worse. And at the beginning, for instance, POD is completely wrong. You make something like a 20, or here you make a 50% error with 5 POD modes. And locally linear embedding always outperforms our POD modes and some other modes which I don't want to discuss. So at the end, after 30 years of research, the solution of reduced order modeling is very easy. You determine your feature space. Then you make k nearest neighbors from your feature space to your snapshot data. And if you want to know the dynamical system, very easy. You look at the evolution of your data and reproject it in your feature space. You have a dynamical system here, and then you do k nearest neighbors on the evolution in your feature space. So 2 times effectively linear interpolation solves the reduced order modeling problems. This is as cheap as it can possibly get. And if this approach does not work, something is wrong with your data, or something is wrong with your model identification approach, or you have inserted a lot of prior knowledge. So now we go to another model, cluster-based model. So this is fully automated, and I want to give you now an appetizer. Okay, I know the problem, so let me